Alright, this video is going to help you determine a molecule shape based off vsepr, or the valence shell electron pair repulsion theory. So we're talking about electrons in the outer energy level. We're talking about pairs of electrons always with bonding. We always talk about pairs. And electrons, since they're all negatively charged, do repel each other. So the basis of this theory is that pairs of electrons are going to be as far away from each other as possible due to that repulsion, and that's what helps determine a molecule's shape. So in this class we have a couple of different options. As atoms get bigger, it's possible to have more than 4 electron domains around a central atom, but we aren't going to get into that for this class. Using this chart, if you have 4 electron domains around the central atom and no lone pairs, you're going to have a tetrahedral shape. So for right now, we're just going to have generic atom X. And let's draw what that would look like. If you have a Lewis diagram or Lewis dot structure that has 4 electron domains, so 1 domain, 2 domains, 3 domains, 4 domains, and none of them being a lone pair, that's going to result in this tetrahedral shape, always. So to draw it, I drew it 2-dimensionally. To try to draw it 3-dimensionally, it's hard. You actually would draw it something like that, whereas this one and this one, this bond and this bond are flush with the board, and this one's coming out of the board and that one's going into the board. If you were to draw 3-dimensionally, to be 100% correct, you would draw it like this, and that one actually would be dashed lines. You don't really need to worry about that. I want you to be able to recognize the shape, not to be able to draw it. Drawing it is a challenge, as you can see. Alright, so what this column looks like, where you'd end up with a pyramidal shape, you need 4 electron domains. So with our generic atom X, we need 1 lone pair, and you would have 3 bonds around the central atom. So electron domains, we have 4, because this lone pair counts as a pair of electrons around this atom. We have 1, 2, 3, 4 areas of electrons around the central atom and 1 lone pair. Students often don't want to count the lone pair as an area of electron domains. This doesn't say number of bonds around the central atom, it says area electron domains. So that includes both bonded and non-bonded electrons. For a bent shape, we need to have 2 lone pairs and 2 bonded pairs to end up with a bent shape. So if you have a molecule that looked something like that for your Lewis structure, here we have 1, 2, 3, 4 areas of electron domains, and 2 of them are lone pairs, that molecule would be bent. Trigonal planar, you have 3 electron domains and 0 lone pairs, so that tells you that you have 3 bonds around that central atom. So you would just have something that looked like this, and that would end up with a trigonal planar shape. And lastly, if you have 2 electron domains around a central atom and no lone pairs, I need the eraser. That's not right. So if you had 2 electron domains around a central atom and no lone pairs, you would end up with a linear or a straight molecule. So in order for that to work and have the atoms be stable, you would end up with something like this. So double bonds count as 1 area of electron domain. So this is 1 area and this is a second area. So going back to our Lewis dot diagrams, as far as those rules are concerned, this atom X has still obeyed the octet rule because it has 2, 4, 6, 8 electrons but it only has 2 areas of electron domains, which would give it a linear or a straight shape. The classic example for this is actually carbon dioxide, because carbon dioxide looks like that. And drawing that makes me realize with a trigonal planar, one of these actually is a double bond, because this hypothetical element X still needs 8 electrons to become stable. So we would have 3 electron domains, 1, 2, 3, even though there are a total of 8 electrons around that central atom. And that is the basis for how you determine molecular shape using the vsepr theory.